Hi guys, it's Max from 3A, and today I'll be covering the 3 topics on your quiz tomorrow. So the first topic is finding the sample size. The second topic is changing the sample size and how it affects the confidence interval. And then the final topic is using panic for means. So right on to the first topic, we have finding the sample size. So I think the best way we could approach this is by doing a problem. So a problem could be 54% of people are sad. And then you could have what sample size n would guarantee a margin of error of at most 0.3, and all this is with a 95% confidence interval. So what you need to do is you need to realize that this is a proportion problem since we're dealing with percentages. So we need to use the proportion confidence interval formula, which is p hat plus or minus c star the square root of p hat times 1 minus p hat over n. So what we need to do is we need to isolate the margin of error from this. So we know this is the point estimate and this is the margin of error. So we just need to isolate the margin of error. So we need to set 0.3 since it needs to be at most 0.3. So we don't want anything less than 0.3. 0.3 equal to our margin of error, which is z star of the square root of p hat times 1 minus p hat over n. So what we can do from here is we need to solve for n, so we need to find some values and plug them in. So we know for p hat, and the problem it says we have a 54% people that are sad, so we can just plug in 0.54, and we can plug in 1 minus 0.54, which is 0.46. And then we know the confidence interval is 95%. So I know for proportions what we need to do is we need to go to second vars, scroll to inverse norm. Since this is important proportions, you use inverse norm. So once you open inverse norm, you have an area. So for your area, you just put 1 minus the confidence interval over 2. So our confidence interval is 0.95, so 1 minus 0.95. And I would put this in parentheses, 1 minus 0.95 over 2, and you leave u as 0 and the standard deviation as 1. So once you do that, you would get negative 1.96. And you can just convert that to 1.96. So you know your z star is 1.96 for this. So from here, I would just plug in your stuff. You have 0.3 equals 1.96 times the square root of 0.54 times 0.46, so 0.2484 over n. So we can solve for n and see what sample size would give us a margin of error of 0.3. So doing this, we can divide both sides by 1.96, so we get 0.3 over 1.96, which gives us 0.153 equals the square root of 0.2484 over n. We can square both sides, and then we have 0.153 squared, giving us 2.3409 equals, we just get rid of the square root, 0.2484 over n. And then using some fun algebra, what we can do is we can move the n over to this side and divide by 2.3409. So our final answer would be 0.2484 over, and I lied to you, I accidentally squared 1.53. You actually need to square 0.153, so 0.153 squared gives us 0.023409, so you would just put the decimal there. So we have 0.2484 over 0.153 squared, which is 0.0234 equals n. So our n would be these values, 0.2484 over 0.0234, which is equal to 10.6. And then you always need to round your n up, because if you round it down, it's going to produce a value that when you divide by n, it'll be less than 0.3. So rounding this up, we get n equals 11. So that would be our final answer. So there are some special cases to consider. So if it's like, instead of giving you a margin of error, you get a confidence interval, it could say something like, instead of saying margin of error, it says confidence interval from like 0.51 to 0.57. So when it gives you a confidence interval, you need to use the formula to find the margin of error, which is the upper bound, which in our case is 0.57, minus the lower bound, which in our case is 0.51, divided by 2. And then when you do this, you get 0.57 of just 0.6 over 2, which is 0.3. So now that you have a margin of error, you can simply isolate it and plug it in all the way back there and go from normal. And then the second case we need to consider is if they don't give us a p. So what p do we use? So we would want to use a p that maximizes this value on top, because we want to have the largest possible thing. So quite literally, if they just don't give you a proportion, what you should just memorize is you should put p as 0.5. So what this is essentially saying is that it's going to give you the largest value for 0.5, or just p hat times 1 minus p hat. So you can try this in your calculator. If you get 0.5 times 0.5, you get 0.25. And if you try like 0.6 times 1 minus 0.6, you would get 0.24. So it's like 0.5 is giving you the maximum value for p hat times 1 minus p hat. And since you're looking for this maximum value, since you're trying to maximize this, you would put 0.5 and then you would solve for n from there. So the next case we got going is the changing sample size and the effect on a confidence interval. So quite literally, we can just analyze this through the two formulas. So we have p hat plus or minus z star square root p hat times 1 minus p hat over n, and that would be for proportions. I would memorize that. And then for means, for confidence intervals, we have x var plus or minus t star, the standard deviation of the sample over the square root of n, and that's for means, so I'd memorize that. So what we can do is, since we're only changing the sample size, it's just this n on the bottom, nothing else is changing. So when we change this n on the bottom, we get a bigger denominator in our fraction. So when you get a bigger denominator in your fraction, it's going to make the overall value smaller. So it's like 1 over 1, 1 over 2, 1 over 3. As your denominator is getting bigger, the value of the fraction is getting smaller. So translating this back, as you're increasing n, it's causing your fraction to get smaller. And then this, which is your margin of error, remember margin error, point estimate, this would make your margin of error smaller, which would just make your confidence interval smaller. So therefore, when you increase the sample size, the confidence interval goes, or like gets smaller. So finally, we have to apply panic to U. So I think we should do this through a problem. So we have a random sample of size 57, and we find the average to be 43 of the sample, and then the standard deviation to be 12 of the sample, and then it asks us to construct a 95% confidence interval. So I'm just going to highlight some values. We know that the sample size is 57, and we know that the average from the sample was 43, and we know the standard deviation was 12. And we want to construct a 95% confidence interval. So for panic, the first thing we do is p, and p is literally just identifying the parameter. So for sample means, we want the true value of the mean. So what we do is we state, let u be the true average, and then you would say something. So if this was a sample of test scores, you'd say the average test score of, and then you'd say your population. So if it was AP students, then you would put AP students. Let's just do that. So average test score of AP students. and then you would need to like state the general population. So you would just say the general population, and it's literally just everything from the population. So in our case, if we were doing AP students and their test scores, the general population would just be all AP students. So that's literally all you need to do for P. It's like let U be the true average. That doesn't change at all, but you would change like test score to whatever is being measured, and of AP students to like whatever is being sampled, and then you would say the general population is all of that. So to A, that's assess conditions. So there are 3 conditions we need to assess. We need to check if it's random. Let me get a better color for this. We need to check if it's random. We need to check if it's independent. And then we need to check if it has normality. So the first 2 are easy. For random, you just literally look in the problem and it says, you just say it's a random sample of, I don't know, what is it, 57, and then you would say whatever, in our case it'd be AP students. And then for independent, you need to use the independence rule, which is 1/10 times the total population size needs to be greater than the sample size. So in our case, the sample size is 43. So when doing like basic multiplication, we can say that the population needs to be greater than 43 times 10, which is 430. So we would just write something like assume population of AP students is greater than 430. So normality is the hard part. So there's 3 ways which we can show that something is normal. So the first way is we use the central limit theorem, and then we say that the n, or the sample size, needs to be greater than 30. So in our case, this is really easy. We know that we have a sample size of, let's see here, 57. So 57 would be greater than 30, and we're all happy, and we can just check it off like we checked these off. So the second way we can do this, if the like population is already known to be normal, then you don't have to do anything. You can just say something like, since the population is normal, the sample is normal, and then you can just check that off too. So the third one is like the hardest one, and you'd honestly hope this is on the quiz. So if n is less than 30, then what you have to do is you're gonna have to like graph your data. So you can do this through like histograms, or like bar charts, or like this weird thing called like a normal estimator. But like, I don't know, I would just graph it in like a histogram right now, because that would be the simplest. So for histograms, what you would want to do is you want to like note that it's like unimodal. You would want to note that it's like symmetrical, and then you would want to note that there's like no outliers. So once you note that, you can say shape is like approximately, or like close enough to normal, and then you would satisfy that condition. So we've assessed the conditions for panic. So moving on to n, that's literally just naming our like what we're doing. So what we're doing in this case is we have one sample. So we have a 1 sample, and then we have a 95% confidence interval, 95% confidence interval for, and then we would just write whatever we wrote on the P, and we defined U. So we would write for U. So what this is saying is like, since we're taking one sample, it's just one sample, and then we have our 95% confidence interval, and then it's for U. And then remember, we define U as like the true average test score of AP students. So that's quite literally pretty easy step. So you move on to I, and this is where it gets fun, I guess. It's where you actually apply the formula. So this formula is basically imperative to know, but so when you're doing sample means, you need to do x var for confidence intervals plus or minus t star, and then the standard deviation over the square root of n, and this is going to give you the confidence interval. So we know x var, if we go all the way to the top, the average is 43, we know that the standard deviation, if we scroll to the top again, is 12. And then we know that our sample size is 43. So this last part is the t-star. To find this, you go to second vars, and then instead of clicking inverse norm, which you would click for proportions, you click inverse t, which is the fourth one. And then once you click inverse t, you should get area and df. So the area, it's just like during proportions, except remember we're doing sample means. It's just parentheses 1 minus the confidence interval. So 1 minus whatever our confidence interval, it's 0.95 in our case, I believe. Yeah, it's 0.95 over 2. And then for degrees of freedom, what you do is you subtract the sample size minus 1. So when doing this, we look back, our sample size is 40, not 43, it's 57. Am I tripping? So like our sample size is 57, so it'd be 57 minus, or yeah, just write n. It's late at night, so we have n minus 1 and 1 minus %, so area 1 minus 0.95 over 2, and then sample size is 57 minus 1. So once we paste this, we get negative 2.003, so we get t star equals negative 2.003. So going back to this, the random sample size is actually 57 because it says it up there. I just messed up, so n is 57 here. Our standard deviation is still 12, and our x is 43. So now that we have 43 plus or minus negative 2.003 times 12 over the square root of 57, we plug this all into our calculator. So I'm going to find the margin of error, 2.003 times 12 over the square root of 57. I get 3.18. So you just add 3.18 to our point estimate of 43. So 43 plus the answer gives us 46.18. And then 43 minus the answer gives us 39.82. So this is our confidence interval. It's from 39.82 to 46.18. So finally, we just need to do the C, which is the conclusion. So this is quite simple. You just say we are, and then you would say whatever percent confident. So in this case, 95% confident that the true average of, and then you would say whatever your sample is, so it's AP students for us, AP students, and then you would say what you're measuring, so it's, I think it's like scores or whatever, scores, and then you would say is between, and you would look at the confidence interval you calculated, and for us it's between 39.817 and 46.18. So from here, we just have panic. So I'm just going to do a quick recap. A random sample of 57, and we find the average to be 43, standard deviation 12. Construct 95% confidence interval. Let U be the true average of test scores of AP students. The general population is all AP students. Random independent normality, and then you can do this, the normality, through 3 ways. CLT, the population is already normal, and then if n's less than 30, you have to graph it and then identify it. And then one sample, 95% confidence interval from U. And then this super important formula, x var plus or minus t star, standard deviation over the square root of n. And then that'll give you a confidence interval. And then finally, you're just doing, we are 95% confident that the true average of AP student scores is between this and that. So good luck on the quiz. This is a lot of content to cover, so it's very hard.